So we just maybe do a little bit more today. So we have this analysis.
Yesterday, you covered something.
Covered. No, yesterday there was no class. I canceled the class because suddenly I got to know that I had an interview today morning. So I don't carry my phone all day. So at night I just checked the mail and said that there's an interview tomorrow morning. So today morning I just woke up and gave the interview. I gave the interview morning. That's why I said I had to cancel it. But I wanted to sleep early and so on, and get other things in place for them. Yeah. So I didn't do. And there was no class. So there is this analysis of, and that was either pool. I just got to know about it a few hours ago. The analysis of functions. So let us take it from the very basic. So basically, we have this sequence of numbers which we do of which consider when analyzing real numbers. We take sequence of numbers and we study limits and so on. That is how we analyze real numbers. Analysis of the functions. So we obviously know that we have a sequence of functions. We have this sequence of and we have defined a notion of limit. Right. So can anybody review? Let's say that each f is from 0, 1 to r, right? So what is the definition of limit? Can anyone review? What is the because we had two definitions, I think. Definition. I just turn it here. Limit. Yeah. So can anybody tell what does it mean to say that limit this fx is equal to f? I mean fn x is so it's tangent. What's the definition?
So basically, uniform convergence you want, or you want pointwise convergence?
Yes, that's very good. So we had two types of convergence. Right? So one was pointwise convergence. So maybe I'll not ask to review the definition, but I think then it's clear what the definition is. Pointwise convergence, and the other is uniform. Right? And I believe that we know the definition. So this uniform convergence treats the uniform convergence is kind of like it treats the functions as points, right? It has that feature in the definition. It treats the functions as points, and it has that definition of convergence.
Actually, you can assume it like a sequence.
Yes, exactly. Yeah, that's what I'm saying. You mean like the sequence of functions?
Like you fix a point, and then only one thing changes. And if one thing changes, we can have a pattern, and we can define a function on that change. So, for example,
no, that is pointwise convergence, or
I'm talking about pointwise convergence.
Okay. Yes. So pointwise convergence is the first type of convergence, which is a straightforward thing. As it fix a point and it becomes a sequence of numbers, right? But uniform convergence is sort of like it treats these functions as one thing, right? As like one atomic thing, right? And that's the philosophy on which that limit definition is made, right? So those are the two subtle differences. And obviously, pointwise convergence implies uniform convergence. No, sorry, I mean, uniform convergence certainly implies pointwise convergence, but the other direction is not. And so, what have we seen about pointwise convergence? That if we have seen the following thing, I mean, if each fi is continuous, each fi is continuous, f need not be continuous. Please, can you guys, any one of you give an example? And this was a problem with pointwise convergence. That you're taking a limit, but that limit is sort of existing, but that is not in that same set of class of continuous functions.
Yeah, but that limit will be a number, right? If we
No.
fix a point, if we fix x naught.
No, yeah, you fix x naught, but each fixed x naught it will be a number, but eventually you return a function.
Yeah, so basically we consider the set of x naughts and then we analyze what kind of limits we get.
What function? Yeah, for every x naught you get an output, and that's why so it becomes a function. The limit becomes a function. You compute it pointwise. As a rule, you compute it pointwise, but eventually you get a function because it varies over the points. I want an example, and we have already.
You get a range.
Yes, because the x naughts change, right? And so let's see that through a very simple example, right? Then we will just know. Right? So we have already taken one type of example, but today let's try to take a different example. Otherwise, it's to make it more interesting. Let us take this. Let's take this. Okay. So f and x, just anything I'm taking, so that I also don't know, and it's good for all of them. 1 plus, like it should have n in it, right? Otherwise, it's constant. Yeah. So the domain is 0, 1. So what is the limit? Let's see. What is f? So we will to the pointwise limit, right? We'll compute the pointwise limit. Have you guys not practiced any examples? I thought you guys would ask me some examples. That would have been.
No, like I'm just trying to find some. I'm just putting some values and calculating. Like,
yes, yeah, then you would know.
For 0, it will be 1.
For 0, it will be 1, meaning x equal to 0. No, for x equal to 0, it is 0.
Yeah, and for x equals to 1, also it will be
0. Sorry, 0.
Yeah. So f of f of 0 is certainly 0. What is other f of x?
F of 1 will also be 0, right?
That's right. F of 1 is also 0. So yeah, you can see that, right? Because all you need to do is just put 1, right? And then you just let the n tend to infinity. So I mean, at each point it is 0. In fact, you can check. At each point it is 0. So it is always right. That is the convergence uniform. So I will come back to the continuous example. You have to give me some example. This is not an example. Limit is continuous. But let's ask this question. I mean, is it uniform?
Hmm. One over n. Hmm. I guess it is uniform
Why?
because like we are predicting that the function which it will converge to is f of x equals 0.
No, no, no. Yeah, predicting meaning.
I mean that to yeah. So in order to prove uniform convergence, like the condition is that we have to find a k after we have to find a k for
Mhm.
such that for all n which are greater than k, we satisfy mod of fn of x minus f of x is less than epsilon.
Right.
So I so if I just take if I just take mod of fn of x,
Mhm. Right.
just take mod of, I can just write mod of fn of x as 1 over 1 over x square plus n.
One
So I
over
just take x to the denominator of the denominator. 1
four.
over
Okay.
x square
Okay.
plus n.
Mhm.
Now if you see the denominator, 1 over x square will always be positive.
Right.
So we don't need that. And obviously, so basically if that is positive, then yeah, right. And this will be we can obviously take we can get an case such that after all the n we can have like if we set an epsilon, we can always get a k such that for all n greater than that k, we can this inequality is satisfied.
Yes. One thing maybe I can say is that if you have found the pointwise limit, then the uniform limit, I mean, if it is uniformly convergent, the uniform limit has to be the same thing,
Yeah,
right?
yeah.
So that is the thing that is implicit. And so once you compute the pointwise limit, some work is done. And then we have to
Yeah, but
just,
look, like you predict the limit, right? Kind of.
yes, then you know that if the limit is existing, then it has to be that. But obviously, it may not still be uniform. But if it is uniform, it has to be good.
Hmm.
If it is uniform, this was a simple example, but we have to get comfortable with this thing. Then that's the very, very important thing, which I've realized in interviews also, is that sometimes, I mean, I know a lot of things, I can work a lot of things out, but I'm not comfortable with everything, like the other new thing that I study, let's say in BSc or whatever. I'm not comfortable with everything. So when I have to work it out, I kind of freeze. I'm not willing to. That little bit, hesitancy in that should not be. So
Like I
math.
also don't like linear algebra and all those stuff. I like make I do a lot of laziness while studying that.
So you should, yeah, always. I mean, actually, it's better to not use just sit with just sit with your notebook most of the time. Not even the book. Whatever you have read, just try to work out on your own. Because see, maths is it. Most of it will come out from inside on your own if you try to work. That's the nature of maths, right? Uh, a lot of it that we read in the books, you can actually do it on your own if you just patiently work it. Obviously, you need the book. Yeah, we always want to just sit with the book and just read, or worse, we just want to read on the laptop. Always better to not just sit with a blank sheet and try to work out things on it. That's much more effective. Okay, I mean that's how it was before. Books in like the notes are available, and that was it. And then you have to just work things out on it. Okay, so this is very simple. Now you guys give me some example where pointwise convergence doesn't imply there's an continuity is not preserved. At each point, you can take the limit, but continuity is not this. So one very simple example, but you have to still give me another example. This is just a sample. Huh?
I'll try, right?
Yes. Yeah. So you just think. Let's think.
Okay. So yeah, I'll just change the domain. Can I change the domain?
Yes. Yeah.
So fn of x goes from 0 to pi over
0 to pi over
2.
pi. Okay.
And okay, so I just defined uh, fn of x as sine of x raised to n.
Okay.
Now, what at the end point it will be 1, and everywhere else it will be 0.
No, but this is not a new example, right? We had done x to the n. And this is not a new example, right? It is the same example you are giving, sort of.
There will log to the base n work.
Log to the base n. That is interesting. So that, okay, let us see. So now the domain we have to change. We cannot keep. We have to keep open 0. Is it pointwise convergent? What is the pointwise limit? Let's think about it. If it fix an x naught, is it 0? Is the pointwise limit 0?
Yes, sir. I think it would be 0.
Should be 0. Yeah, because so why is it 0? Because intuitively that's what it feels like, right? That if you take larger and larger, so this, so what power do you need to raise n to get x naught?
If you see the log of graph, then graph of log, then
Oh, I don't think like, yeah, but I don't know. It can also go negative, right? It's an interplay between n and x naught. So which is bigger? If n becomes too big, then obviously it will go into negative thing. Like it will be negative, right?
Oh yeah, yes. Oh,
Yes,
sorry.
I
The
think
domain. No, it's less than 1. Yeah, I was taking bigger than 1. Yeah. X naught is less than 1. Okay. Right. So then let us see.
Even then, even if you expand the domain, the same thing is going to happen, right? Because we are like taking x naught is fixed and n will obviously sometime exceed x naught, and when that happens, the log will become negative.
No,
Like
no. Log becomes negative when the domain is less than 1. Otherwise, log will be
yes, sir.
positive.
If this one is less than 1,
That happens. Yeah. That matters. That matters. Greater than 1, less than 1 matters. So let us just compute. So if it is if it is, so let's say x naught is strictly less than 1. So then what happens? So n to the power x naught, no, sorry, n to the power t is equal to x naught. This is less than 1. So as n goes to infinity, where should t go?
Minus infinity.
Minus infinity, or yes, that's right. That's right. Can you prove it? Can you explain us? Yeah, that sounds correct. Can you give
No,
more?
like maybe we can say like this, that okay, so at this point n raised to t, so if we take, let's say, n we increase it by 1, let's say n plus 1, then if we can argue, then t will decrease at that point.
T will,
So t,
yeah, T will certainly decrease.
yeah, so if we can say that, then obviously
No,
it
that doesn't
will
imply it goes to minus infinity.
that does not imply.
Yeah, but you're right. I mean, you can take any t and then you can increase large enough so that it becomes more than x naught.
Yes.
Right, and then it has to go to minus infinity. I think, right? So
It
if
seems.
yeah, so if you take any t which is less than 0, right? So I mean, let's just take t to be minus 100. Right? Now, if I, this is a simple thing, right? But so if I, no, but this is the sorry, this is the decreasing function, right? No, I think we are doing something wrong. Let us just think about this. If n goes to infinity, where does t go? Simple thing, but t is minus half.
Sir, if n goes to infinity, then 1 by n goes to 0.
Right, right.
So 1 by n whole to the power of something should be x naught, some positive thing.
Right.
So, I mean, because this goes to 0, you have to. No, actually, it should be maybe going to 0 itself, because
Yes.
when a number is half or 1/4, if you square it, it just increases. I mean, it reduces. So you maybe have to square root it.
Yes. So I mean, as you increase the n, this is so as you increase the n, right? As you increase the n, which one is bigger? Yeah. So the number is less than. I mean, I just
1 by n only will be bigger. 1 by root n plus 1 is more than n. So root n plus 1 is more than root n. No.
So let us just compare it. So we have this. This is bigger than, this is bigger than 1, right? Yeah. So this one is bigger, right? Yeah. So I mean, as the so what is happening? This one is yeah. So let's just work it out on a fresh page. Yeah, just join once again. Just work this out. I don't know what that. Yeah, just join once again for 5 minutes.